Hello everyone, welcome to the class. Today we will start with multirate signal processing. We will have a introductory session and we will see how we will see the mathematical perspective behind multirate signal processing. There are two operations which are important in multirate signal processing. The first is the upsampler or interpolation, and the second is downsampler or decimation. So let us start with what is an upsampler. The upsampler is actually represented by this diagram. Let's say this is the input signal, and we upsample the sampling rate of xn, which is the input signal, by let's say a factor of 2, then yn is the output. So that means the sampling rate of yn will be double the sampling rate of xn. Now it is mathematically defined by this equation: yn is equal to x of n by 2 for n even and is 0 for n odd. Now the usual notation of the upsampler is like this: yn is equal to arrow upwards 2, because we are using here an upsampling by a factor of 2. In general, we can have some other factor. We can put it L or M, that we will see, of xn. Now the upsampler simply inserts how the upsampling will be achieved, because the sample rate of yn will be double the sample rate of xn. In that case, let us say xn is the input signal, and the origin of this discrete sequence is at 5. The origin value is 5. The upsampler simply inserts zeros between samples. For example, if xn is the sequence, and if we have to upsample by 2, in that case we will insert 2 minus 1, 1 0 between each sample. And if we have to upsample by 3, we will insert 2 zeros. Like that, we will insert 0 before 3, we will insert 0 before 5. So between every two samples we will insert 1 0, because we are upsampling by 2. Now given xz means the z transform of xn, we will have to see what is yz. In that case, xz, if we take the z transform of this equation, we will get this 3z, because this is at sample value n equal to minus 1, so sample value is 3. In that case, you will get z here 5, because this is the origin, 2z to the power minus 1, and so on. Right. So and we can also get what is yz. If you compare xz and yz, what you see is yz is the z transform. We can have the notation like this: is equal to x of z square. It is very evident from here also, right? Because this is the xz is the z transform of xn, yz is the z transform of yn in the example that we are taking, and therefore we get the equation like this: yz is x of z square. All right, and we can also derive the equation. This is the z transform of yn, and you replace yn with x of n by 2, and you get x of z square. You can derive the relation mathematically also. Now if we see the upsampling effect, the Fourier transform of a signal, how do you get the Fourier transform of this yz? You simply replace z by e to the power j omega. Small omega is the digital frequency. So once you replace this, you will get e of j to omega. Y of e to the power j omega is x of e to the power j to omega. And we can also use the notation by putting Fourier transform like this, and we will say that Fourier transform y omega is equal to Fourier transform x of 2 omega, right? Now the theory that we have discussed till now is for the case when the upsampling is done by a factor of 2. Now if we look at in general the case of upsampler, let us say we take the case of n L-fold upsampler. That means we are upsampling by a factor of capital L, represented by the diagram. So xn is the input signal again. We are upsampling by a factor of L, and yn is the output signal. And in general, we have already done with an example by taking the interpolation or the upsampling factor of 2. But here we are taking a general case, and we say that if the upsampling is to be done by a factor of capital L, then yn will be given by this notation. We can use this type of notation for saying that we are doing upsampling is x of n divided by capital L, when n is a multiple of L and 0 otherwise. And if we go further, the L-fold sampler simply inserts capital L minus 1 zeros between samples. Let's say this is my xn, and if I choose, I have already taken this example. If we choose capital L equal to 4, then we will insert 3 zeros between each sample, right? And we saw that in this equation, we saw that this yz is equal to x of z square in the case when the upsampling factor is 2. But in general, if we take the upsampling factor of capital L, in that case we can generalize the concept and we'll say that yz is equal to x of z to the power L. And if we replace z with e to the power j omega by to have the Fourier transform, so y of e to the power j omega is x of j omega L. And we can also represent Fourier transform y omega is equal to Fourier transform of x Fourier transform of x L omega in general. This equation actually shows that the L-fold upsampler will create capital L minus 1 spectral images, right? For example, when a signal is upsampled by 4, there will be 3 spectral images. We will discuss in my next lecture the details, and we will see graphically how these images are created, how you will have to how you will low pass filter to create an interpolator. You will see in the next lecture. So the main point we take here from here is that the L-fold upsampler will create capital L minus 1 spectral images, and that's what is said here in the remarks section of this presentation. No information is logged when a signal is upsampled. So you're doing the upsampling, you are rather inserting the samples, right? So no information will be lost. The upsampler is a linear but not a time invariant system. The upsampler introduces spectral images. So that's the takeaway from understanding the theory of upsampling. Now let us take a look at what is the downsampler. The downsampler is represented by the following diagram, where xn is the input signal and down arrow with a factor of 2. Similarly, we are considering the downsampler also with a factor of 2 only, and we will derive the equations and we will generalize the derived equations for a general case of downsampler factor, right? Any general case of downsampler factor. So xn is the input signal, yn is the output signal. We are considering a downsampling by a factor of 2. So it will be defined as the downsampling can be defined as yn is equal to x of 2m, whereas in the case of upsampling it was n by 2. Now the usual notation as we were doing for the upsampling, the arrow was upwards, now the arrow will be downwards. Yn is equal to down arrow 2 x of n, right? Now the downsampler simply keeps every second sample and discards the others. So in the downsampling we have to actually reduce the sampling rate. How to reduce the sampling rate is that since we are doing the downsampling by a factor of 2 in this example, we will discard one sample between every one of the samples we will discard. For example, between 7 and 5 we will discard this 3. Between 5 and 9 we will discard this 2. So that's what is set here. Yn downsampling by 2 of xn is given by 7. One sample is discarded after every next sample. All right. Now, the same thing, in the same fashion, we will try to derive the equations. We will take the z transform of xn. The z transform of xn is given as, because 5 is the origin, so it will be 3z and 7z square. 7z square plus 3z plus 5, because here it is z to the power 0. Now comes as 2z to the power minus 1, 9. Like that, we will get the z transform of xn. Similarly, we will get the z transform of yz, uh, 5 being the origin. So this equation we will get after taking the z transform of yn. Now, again, if you compare the equation xz and yz, you will see that how can we express yz in terms of xz. Let us see how this yz can be expressed in terms of xz. Consider the sum. Let's say we take two equations. One is of x, one is with x of z, and the other is x of minus z, and we take the sum. Now that x minus z will be given by, so what will be x minus z? X of minus z will be given by this equation. So because you replace every z with minus z, so z replaced here with minus z will give z, because it is square, 7z square minus 3z, and so on. Like that, we will get the equation. And if we take the sum of xz and x of minus z, we will get this twice of 7z square and so on. Right? What is this part? Twice of, this is actually yz square. If you look at yz is what? 7 excuse me, 7 7z plus 5, 9z minus 1. So if you take the square of z, you will get 7z square plus 5 plus 9z. So that means x of z plus x of minus z is equal to twice of yz square. That this equation we get. And what is yz? Yz will be equal to x of z to the power half plus x of minus z to the power half divided by 2. Now this is very important to look at this equation, because this equation will correspond, this part of the equation will correspond to aliasing. All right. How does downsampling affect the Fourier transform of a signal? Let us see how it affects the Fourier transform of the signal. We have already driven with this equation, yz is equal to x of z to the power half plus x of minus z to the power half whole divided by 2. Once we have to, if we have to go for the z transform, we will replace this z with e to the power j omega. So this equation will be replaced with z is equal to e to the power j omega. You do the manipulations further into the equations, so you will get this equation, half into x of e to the power j omega by 2 plus x e to the power j, the space factor will be omega 2 minus pi, and we can also express this half Fourier transform x of omega by 2 plus Fourier transform x of omega minus 2 pi by 2. Right. So actually this is the equation that we will get after after taking the Fourier, after analyzing the Fourier transform of yn. Now we will in my coming lectures we will discuss about the spectra of these signals in detail. Now, what is the general case of here? In the previous the slides, what we have taken is, we have taken a case of downsampling with a factor of 2. But let us now try to generalize the whole derivation, and we will say that if the downsampling is done with a factor of m. Now xn is this input signal given to a downsampler, right? Which is doing the downsampling by a factor of m, and yn is the output signal, and we can express this a downsampling case with the mathematical definition as yn is equal to x of mn. All right. Then the m-fold downsampler keeps only every mth sample and rest will be discarded. For example, we have already seen with the case of capital M equal to 2. For example, if this is the sequence, and now let's take the case with M equal to 3. So every 2 samples will be discarded. So 8 will come here, 7 and 3 will not come, 5 will come, 2 and 9 will not come, 6 will come, and so on. If we do the downsampling with a factor of 3. So similarly, we have in general we can say that as we derived the YZ equation for capital M equal to 2, that means downsampling by 2, we can generalize the equation and we can write the equation like this. If you so this is the equation. Yeah, this is the equation where YZ is given by this, because this 2 is coming because we are considering a downsampling case with capital M equal to 2. Now if we are considering M, so we will get this equation. All right, where so 1 by M and so on, where W is given by e to the power j 2 pi by capital M. And if you replace this W with if you substitute the value of W here, you will see that at every 2, that means with the downsampling factor of 2, you will see that M is coming, capital M is coming, and that gives us a general case of downsampling when you're doing the downsampling with a factor of capital M. So we can say that this is the Fourier transform y omega is DTFT of this downsampling by M of xn and xn. Like this, we can represent the Fourier transform, and this will be given by this equation. Now, in general, we can make some remarks about downsampling. In general, information is lost. Why information is lost? Because we are losing the samples, right? And when a signal is downsampled, the downsampler is a linear entity, linear system, but not a time invariant system. All right. So in general, the downsampler causes aliasing. So the effect of downsampling is aliasing. If you remember, the effect of upsampling was imaging, right? We will discuss in detail about how to deal with this imaging concept and aliasing concept in upsampling and downsampling, and how an upsampler can be converted into an interpolator by the introduction of a low pass filter, and how the downsampler can be converted into a decimator by again the introduction of a low pass filter, and how the low pass filter deals with the effect of imaging and aliasing. We will discuss in detail. Okay, now let us take an example where we will use the formulas derived for downsampling and upsampling, and we will try to solve the problem. The problem at hand is to express the output yn of the figure below as function of the input xn. By simplifying the expression derived, we will have to show that yn is equal to xn minus 1. Now let us look at this problem. The problem is we will start from here, from this end. Xn when delayed by 1 unit of time will give us Pn. So Pn is equal to xn minus 1, and we take the z transform. Pz is xz of z to the power minus 1. Now we can also say Pz to the power half is equal to xz to the power half, z to the power minus half. All right, and we can also, and this also implies that P of minus z to the power half is equal to x of minus z half, power half, and minus 1 we take out, and z to the power minus half. Then W, and what is Wn? Wn after downsampling Pn by a factor of 2, that means Wn is equal to P of twice n, and once we take the z transform, Wz will be equal to this formula. This we have already derived, and we now have the value of pz to the power half and p minus z to the power half, and we express wz in terms of xz, and we get this formula. Ultimately what we have to do is we have to, as the question says, that yn has to be expressed in terms of x and in terms of xn. So that's what we are trying to do. So we reach to this point where the z transform of wn, and we have expressed it in terms of xz. Now let us look at Vn. Vn is equal to x of twice n, because there is a decimator by 2. Then V is, once we take the z transform, we know this formula is half of xz to the power half plus x of minus z to the power half. Then we come to Qn. Qn is what? Here it is upsampling. Once it is upsampling, we know the mathematical relation of upsampling when it is to be upsampled by a factor of 2. Qn is equal to V of n by 2. We take the Z transform, we know that we've already done it. Qz is equal to V Z square. And what is uz? Uz is only this delayed version of Qn. So that means uz is equal to qz z to the power minus 1. Okay. So similarly, we can go for this rz also. Rz, because wn is upsampled by 2. So once it is upsampled by 2, rz will be equal to wz square. Right, now we know what is qz. We have we can substitute the relevant expression. So rz we have uz is equal to, we've already seen previously, and we can further solve this whole sum, and we will see that yz is equal to uz, because yz is equal to uz plus rz, and we substitute the values. Finally we get yz equal to xz of z to the power minus 1, meaning by this z transform equation is expressed in terms of the difference equation in terms of yn is equal to xn minus. That's what we wanted to actually prove. The original signal xn is reconstructed. The above structure is a perfect reconstruction system. So that's how we can solve various questions once we know how the decimation and the downsampling and the upsampling is carried out, and what are the mathematical relations by which we can use those mathematical relations in our numerical problems, and we can find out, we can further solve the questions. Thank you so much.